You are about to tackle a very complex subject in the world of calculus. I've informally called these accumulation functions, and you may or may not have already learned about the derivatives of accumulation functions. There's a video for that, or you've already covered it in class. If you haven't, you can still absolutely do fine on this, but you might be a little confused when it comes to taking a derivative. Let's not worry about that right now. Here is some function a of x. And right away you would say, oh my gosh, what's going on with this function? It has an integral inside of it. But remember, that shouldn't be that big of a deal, because as you've gone through your math life, functions used to have addition and subtraction inside them. Then they started showing up with things like squares and square roots, and eventually your functions would have natural logs and trig functions inside of them. So there should be no reason why an integral operation cannot be inside of a function. It's really no different than natural log or multiplication or square rooting. So you kind of have to get over that. Now it is a little bit more awkward to use, so let's talk about that. Let's talk about finding the y values. So this graph, which is movable, I'm going to use it as we go on to different pages in this video. This is a graph of f of t. Now that's a little bit confusing because we're working with function a of x. But here's the weird thing. A of x gets all of its y values by finding area trapped underneath f of t. So let's just do one example to begin. What is a of 0? Well, you learned when you were learning about functions, a of 0 means you plug a 0 in here, and if x is 0, that means you plug a 0 in here. So a of 0, I would rewrite to look like this. And now I say, wait a second, that just means travel from -2 to 0 and find the area trapped under f of t. So as I travel from -2 to 0, this region right here is the shaded region. So that's really a rectangle that is 2 by 3. So the answer to a of 0 is 6. Or in other words, if I felt like it, I could start making a t-chart, and if x equaled 0, y would equal 6. We've plugged in a 0, gotten out a 6. So different, but different operation, but really the same thing you've always learned with functions. Let's look at the next one, a of -5. That means we're putting a -5 there, which means a -5 goes there. So now be careful. We're traveling from -2 to -5. So we're traveling in the negative direction, and the region is above the axis. So I've got myself some sort of a rectangle. Well, actually it would be a square. As I travel from -2 to -5, I'm going to count that like a -3. The height is a +3. We get a -9. So plug in a -5, get out a -9. So making a t-chart or finding y values for an accumulation function usually boils down to just integration. We're going to do 2 more, and I'm going to pause this while I fill these 2 out. Let's look at these last 2 because they involve a little tricky thing. This piece right here, it says is a quarter of a circle of radius 3. So you have to imagine that if I would draw a full circle there, this is 1/4 of that circle. So when you ask for a of 3, it's the integral from -2 to 3. Well, we already know the integral from -2 to 0 is this rectangle that we did earlier, so that's worth 6. This is a quarter circle, so 1/4 pi r squared. I do all that math and I get this y value. And finally, if I go a of 9, That means I'm traveling from -2 all the way to 9. I've already done the -2 all the way to 3. That's the 13.069 that I just figured out. And then you would have this additional piece, this triangle down here, which is 6 units long and 3 units negative. So that's 6, and it goes -3 below the axis. So base times height divided by 2, and I put those two together and I get that y value. So you can see that if you were determined enough and had enough time, you could make a complete t-chart and you could get a picture of what a of x looked like. It probably would be curvy, it would have maximums, minimums, concavity. My oh my, this sounds like curve sketching is in your future. Before we get to any curve sketching, let's leave the example we've been working on and let's just look at this. I made up a brand new accumulation function, w of x, and this function's got a lot going on. It's got some multiplication, it's got some addition, and it also has some accumulation. So just to show you how this works, if I asked what is w of -1, that means I'm plugging in a -1, which means I plug in a -1, nothing to plug in there. And now if I'm plugging in a -1, that means that is 3 times -1, or -3. Now f of t is this graph I've been looking at. Let's see, can I get these both in here? Pretty much. So this is really a -4 plus 3. And now I would need to figure out this piece. It says I'm going from -2 all the way to 3. And we learned earlier that was a 13.069. And who cares what this number works out to be? We'll just call it a number. The point is, plugging in the -1 can be a little bit awkward, so just be careful. All right, we're going to move on to different ideas because at this point in the game, we say, hey, you know how to find y values of accumulation functions. I'm keeping the same accumulation function, the same graph of f of t, and now we're going to start looking at some other aspects, not just y values. So we say, is a of x increasing or decreasing at x equals 2? Well, remember, this is a graph of f of t. So I would really probably have to do an intensive t-chart and get a good graph of a of x to answer this question, and that seems like that would be a rough process. So this is where the derivatives of accumulation functions come in. Here's my a of x, and if you know your derivative rules, you know that the derivative is really easy. Since this goes constant to variable, I just plug that in. And here's what this means. Function a of x, which I probably don't even know what that thing looks like, its derivative is f of x, and that's really right there. I know this says f of x and that says f of t. We're just going to have to get over that. So if I want to know anything about the increasing or decreasing nature of this, that's its derivative, I just look at this. So if they ask me if a of x increasing or decreasing at x of 2, I say, hey, why don't I figure out the derivative at 2, which is really f of 2, and f of 2 is a positive number. I don't know exactly what that is, so I'm just going to estimate it. I'll call it a 1.8. What I really care about is it's positive. So I would answer increasing because a prime of 2, which is really f of 2, is greater than 0. Here's a picky little AP point. You might feel like saying increasing because a prime of 2 is greater than 0, but because a prime of 2 is connected to f of 2, they want you to write that both of those items. So I know that's a picky thing and you may forget it, and they may take off a point if you forget it. All right, so now this next question, what is the slope of a of x at x equals 6? It's very similar to that one. So that means I want to know what is a prime of 6, but a prime of x is f of x. So that says a prime of 6 is really f of 6. And at x equals 6, f has a value of negative 3. So my slope is negative 3. By the way, you might be thinking that's a non-differentiable point, but that's a non-differentiable point for function f. So f prime of 6 does not exist, but f of 6 does exist, and f of 6 is what represents a prime of 6. Wild and crazy, huh? Well, the next two questions, you don't see them yet, but they're going to involve the second derivative. So let's go back up here. If I take the derivative of the left, I take the derivative of the right, that tells me the concavity of this thing is based upon the slope of that thing. Very important to write these down on your paper. As soon as you start an accumulation function problem, write down the first two derivatives. So using this piece of information, says what is the concavity of a of x at x equals 7? Well, concavity is a double prime of x. I have to show the AP grader that I understand that a double prime of x is really f prime of x. Or more specifically, a double prime of 7 is f prime of 7. And what they're basically saying is, at 7, what is the slope of this thing? We're on a segment of positive 1. So I have a concave up. Because a double prime of 7, which is f prime of 7, is positive. Let's look at this. Does a of x have any points of inflection? That would mean a double prime of x switches sign. But we know a double prime of x switching sign based on the derivative. I'm using that. Means f prime of x switches sign. Which means, does the slope of function f ever switch sign? Well, the slope is 0, then the slope starts being negative. That doesn't really mean a sign switched because 0 isn't positive or negative. It's kind of weird. So now I'm negative sloping, positive sloping. At x equals 6, a double prime of x, which is really f prime of x, switches sign. So I would say inflection point at x equals 6. So notice that everything that we've answered on this page was directly related to this. The big idea is this. You don't know what a of x looks like. This is way too complicated for most human brains unless you're a freak. But you can answer questions about it by knowing the derivative relationship, and that almost always allows you to look at the graph of f of t and come to really easy decisions. I promise you that this is the last page of this accumulation function stuff, and I know it's a long video, but this is a deep concept. Same accumulation function, same graph f of t. Like I said, you are very smart to put this on paper so you have it handy. And what we're going to do now is the official curve sketching procedure that you learned earlier in the year. The First step for curve sketching is do a first derivative number line, which means my first derivative is f of x. So what I would do is I would say a prime of x equals f of x. And now if you recall, what goes on here is when a prime, or in this case f of x, equals 0 or undefined. So in this case, f of x is never undefined. I know its slope might be undefined, but it is never undefined itself. It does equal 0 at x equals 3 and x equals 9. This drawing might not be to scale. Oh, looks like we're going to go, let's go to 10. So I'm going to call this 10. Which means we get to put a 9 right there. Now you would do test points. The test points mean take something in between. So between 3 and 9, let's choose a 5. At x equals 5, a prime of 5 is f of 5. F of 5 is a negative value. So that means any number I would have picked in there would have given me a negative. I'll test 9.5 in here. That's a positive. And between -5 and 3, maybe I'll test x equals -1. At x equals -1, a prime of -1 is f of -1, which is a positive value. So by the way, by doing this, I now know that function a of x is upward sloping, then downward sloping, then upward sloping. So I'm starting to get an idea of what a of x looks like. I'm going to do a double prime of x now, and we know a double prime is f prime because of this derivative relationship. So I'm really going to look at the slope of this. So we have some weird stuff happening. From -5 to 0, my slope is 0. So that's never happened to us before, so I'm just going to put zeros in there. From x equals 0 all the way to x equals 6, a double prime, which is the slope of function f, is negative. And then from 6 to 9, actually 6 to 10, the slope is positive. So what that means is I've got a stretch of concave down, I've got a stretch of concave up, and when the second derivative is 0, there's no concavity, which means we have a linear stretch. It might be increasing or decreasing, but it's linear. So we filled out these two number lines, and at that point, just like we would have done in a normal problem, at that point we can answer questions. So a of x, which is this function that we don't necessarily know what it looks like, at x equals -4, which would be right in here, I would say it is increasing. And if I had to justify that with AP language, I would have to say this. A prime of -4, which I have to show that I realize is connected to f of 4, and I just say that's greater than 0. Remember, you got to connect those two if you want full AP credit. Next question. At x equals 3, is there a maximum or a minimum? If I filled out this number line, it's so obvious. It was going uphill and downhill, that's a maximum. And then I would say because a prime of x, which is the same thing as f of x, switches from plus to minus. And finally, we covered this one already, but there's a point of inflection that tells me to look at the A double prime. The justification for a point of inflection is A double prime switches sign. I can't call that a switching of the sign. That's a little bit awkward, I know, but it definitely can call that. So at x equals 6, because A double prime of x, which is the slope of f of x, switches sign. The key to doing any curve sketching questions with something that you don't know what it looks like in an accumulation function is get those derivatives down on paper, and then all of a sudden you can use this graph to easily fill out a number line and easily answer any questions. Thanks for sticking in there. This was a deep concept. It's worth it though. The AP test writers and possibly your future college professors love to ask questions about this.